Planning and executing a rocket launch is normally a slow process, an astronomically expensive and challenging logistical operation. However, last year, the industry took a major leap forward. With only 24 hours notice from the United States Space Force, Firefly managed to integrate a payload into its Alpha rocket, plan its launch profile, get their rocket positioned and fueled on the launch pad, and finally, launched, shattering the previous 21-day record. All in an effort to carve out a niche for itself in the highly competitive space launch market, which is currently dominated by SpaceX. SpaceX is launching more into space than any other company, thanks to reusable rockets driving down the price of launch, but that doesn't mean there isn't space for others in the market. Being able to launch at a moment's notice is a really attractive capability. For a commercial company, say you have a satellite ready to launch that will generate $1 million in revenue every month it's in orbit. The next available launch for a rideshare with SpaceX is 12 months away. That's $12 million of lost revenue. And that's vastly more expensive than the cost of launch for most small to medium-sized satellites. In a case like this, waiting for the cheaper launch price simply doesn't make sense. The cost of opportunity is just too high. Then, of course, there are the military applications, which is why the United States Space Force contracted Firefly for the Victus Nox mission. We don't know what was on board that mission, but we do know why militaries are interested in getting things into space quickly. If an enemy destroys a satellite critical to your military operations, you want to replace it quickly. If a foreign military places a satellite or even a weapon into orbit and you don't know what it is, you want to be able to send something up to take a closer look, or if World War III has broken out, potentially destroy it. Firefly has focused the engineering efforts of their Alpha launch vehicle with this valuable niche in mind, and have come up with some unique designs to put them ahead of the competition. To learn more, I spoke with Alpha's chief engineer, Jordi Garcia.
And one of the mission requirements was responsiveness, and
Correct.
What we're talking about today is how you've designed the rocket around kind of things like the Victus Nox mission of just being able to launch within 24 hours. What engineering designs can you talk about that help towards that mission?
Yeah, so when we conceived Alpha from the beginning, we were really targeting to go quick and be able to actually load, detank, and fly as fast as possible. So for example, some of the requirements is that you want to make sure that you can load your vehicle fast and detank your vehicle fast if you need to, right? Let's say you have to scrap and go the next day. You want to make sure it doesn't take you 12, 16 hours. So there's a lot of design decisions that you need to make from the beginning, making sure that your quick disconnect lines, your fill lines are sized, your vent lines on a way that you can fill. My target is 30 minutes. When I started, it's like, engineers, in 30 minutes, I want a vehicle ready to go, right? On like, loaded.
Is there any difficulties around that of pump rates and volume? Is there any like hard limit you hit that, or is it you can just size the pump as big as you want?
No, you can, because at the end, what you want to get is the most mass to orbit, right? So the problem is the bigger I make the lines and the quick disconnects and the valves, the heavier it gets,
okay.
Right? So it's a challenge. If I could load it in 18 hours, I could go very slowly and fill it up, things would be lighter. But then you got to make that trade. It's like, okay, I'm having lines and valves and components that I can take to orbit and not eat too much performance, but still at the same time be able to fill and detank quickly. It sounds silly, but one of the requirements that we have is like operators cannot work more than 12 hours a day, right? So if we want to load, detank, go to sleep, and then go again next day because you have a scrap or you got to change something, we need to be able to squeeze all that timeline and make it in less than 12 hours to be able to get crew rest and then go again the next day.
Okay.
Right? So it's something that, and still now we're still polishing. The more we load and detank and fly, we learn there's things we can improve. So we have a lot of design changes coming up to, maybe not a lot, but we have some design changes to try to improve our timing.
And the temperatures of your fuel and oxygen are different, right?
Correct. Yes. Our liquid oxygen, it's roughly minus 290 F, minus 300 F. That's one big difference that we have from SpaceX, for example, that we are not super cool. We don't actually chill the liquid oxygen to get it even cold to get more performance, right? We just get it up to the vehicle and we let it vent to a saturation. And at those temperatures, at those pressures, you achieve the temperature that you want.
What are the pros and cons of that?
The pros of that is that, let's say, if we want to hold and wait, you can hold and wait, right? If you're super cool, because you had to go through a liquid nitrogen system, right, you can load and then you have more performance, right? You get can't remember how much. You get an extra density from that, but you gotta go, right? If you wait 30 minutes, 45 minutes, don't know exact timings, but something like that, then you have to detank and you have to scrub for the day. And for us, as we wanted to make sure that if you had, I don't know, a ship or a delay for any reason, that you could still go in an hour or so. So you're taking that performance hit, but you're getting some more launch availability from that time.
So, Firefly is balancing performance and launch availability. They have larger fuel and oxygen lines to allow them to fill their tanks quicker, but that means they carry more weight and lose some performance. This compromise was also made when choosing propellant temperatures. SpaceX uses supercooled propellants to gain extra performance through increased density. SpaceX needs to save some fuel to land their first stage, so every bit of extra performance is vital. Firefly has chosen to skip the supercooling step. This brings up an interesting logistical problem with the space industry. There are many reasons a launch may be scrubbed. It's not uncommon for a fishing vessel to stray into the exclusion zone while a rocket is being loaded with propellant. When this happens, the launch has to be held until the boat is cleared. But time is very much of the essence, especially for SpaceX. Their supercooled propellants can't stay supercool forever. So, they start loading propellants 35 minutes before liftoff. They call this a load and go. A delay, like a boat entering the exclusion zone, can be mission critical. As the propellants begin to warm and lose performance, eventually enough performance is lost that they can no longer satisfy mission requirements, and they need to drain the tanks and wait for another launch opportunity. This delicate timing became an issue when they won the contract to launch the Crew Dragon to the ISS. This load and go method had never been done for a crewed launch before. The space shuttle loaded its propellants 7 hours before launch, which gave NASA plenty of time to find issues before the astronauts got on board, and they had concerns about SpaceX's load and go method for crew safety. In 2016, a Falcon 9 carrying a $2 billion Facebook satellite blew up on the launch pad during propellant load. The metallic liner of the composite overwrapped pressure vessel had buckled, which led to the explosion. Had this been a crewed launch, something much more valuable than a Facebook satellite would have been lost. But NASA eventually approved the load and go method after an extensive safety review. While Firefly isn't willingly waiting for 7 hours, their warmer propellants can be continually topped off as they evaporate without losing any performance. This elongates their launch window. We saw this in action with the first Noise of Summer launch attempt on July 1st. When ground equipment failed, the launch was simply aborted, but they simply reset the countdown timer and tried a second time shortly after, while topping up their propellants. Unfortunately, they did not find a solution for the ground equipment issue before the launch window closed, but another opportunity was available the very next day. There are other ways to minimize the chances of a scrub too, by reducing the complexity of the rocket and increasing reliability. The launch of Boeing's Starliner on the Atlas V rocket was scrubbed due to a faulty valve. These are natural issues to have, but being able to prototype and test new engine components quickly gives you a massive advantage in developing a simpler and more reliable rocket. This is one of Firefly's greatest advantages. It's rare for space companies to have test stands close to not only their engineers, but their manufacturing facilities too. SpaceX's primary test site is here in McGregor, Texas. While the majority of SpaceX's engineering staff working on the Falcon 9 and Falcon Heavy are located in California, Blue Origin tests their engines at NASA's Marshall Space Flight Center in Huntsville, Alabama, while their engineering and manufacturing facilities are in Seattle, Washington. Having engineering, manufacturing, and testing separated slows down development and makes it harder for engineers to truly get a holistic view of their job. Firefly's headquarters, manufacturing, and testing facilities are all located just north of Austin, Texas. If you are interested in working with them, we've just updated our jobs board with all of their open positions, from HR to machinist to launch engineers. You can see all of their open roles on startpropeller.com. Firefly's VP of Engineering had 11 different addresses over 9 years working at other new space companies. At Firefly, she needs just one. I joined her at one of their test stands.
Sure. So my name is Bridget Oakes. I'm the Vice President of Engineering here. I've been with Firefly for 5 years. So we're actually on our Test Stand 1 site here. So we have 6 different test stands that test anything from components to full vehicle stages, as well as composite structures. So this specific test stand is an engine test stand. So we've tested Reavers here, Lightnings here, Mirandas here. And what I mean by those engines, on the Alpha vehicle, the first stage is powered by 4 Reaver engines. This is a Reaver engine. And then the second stage is powered by a Lightning engine, a single Lightning engine, which we also test on this stand.
And you're testing the engine here today.
Mm-hmm.
What are you testing? Like, what sort of results are you looking out for?
So this specifically is one of our development engines. So we're testing every day, whether it's this stand or another one. This actually hot fired yesterday, and we swapped some components around. This development campaign, 2 things we're looking for here is improved performance on the Reaver engine. So what we look for there is different designs on the injector to increase that mixing and that C-star efficiency. And then another thing that we're also looking at is improving our reliability on the main valves. So there's some unique differences to the LOX main valve on this engine.
To get into specifics, the video that we're making is about the Victus NOx mission and how a big part of your focus here at Firefly is responsiveness, like quick turnover time. Is there any specific designs with your engines that are designed to help with responsiveness?
Yeah, absolutely. So I think our Alpha vehicle is actually very well suited to responsive space and that market. Most of that, I think, that we pride ourselves on is this tap-off engine cycle technology. So Firefly is the first company that's actually flown this engine cycle to orbit, and successfully so. So what I mean by tap-off engine cycle, there are a couple different open cycles that companies will use. So GG, or gas generator cycles, is fairly common, so that's what Merlin runs on. And then there's also open expander and some other ones. Tap-off specifically is unique when we compare it to the GG cycle, because we don't actually have a separate combustor. So GG cycle has its own gas generator that operates at a different mixture ratio to drive the turbine, which drives the turbo machinery and the turbo pump that takes low pressure propellants to high pressure to combust in the chamber. We don't have that second combustor. So what we actually do is we siphon off a portion of the gas inside the main chamber, and that's what actually drives our turbo pump. And why that's exciting is a GG could be, on a scale of an engine this size, maybe an additional component here that's highly complex, has additional mass. We've essentially replaced that with this 1.5-inch line down here. So this tiny, you can see that that's probably, a couple pounds, maybe a foot long, and that replaces an entire separate combustor. So it pulls off the gas from this chamber up here and then drives that turbine right over here. So it's more reliable, it's a tube, and less mass. So that really helps us put us in a good spot for responsive space types of missions where they really care about that reliability.
That must be difficult. It is so much simpler than having the pre-burners and everything and having those additional parts. There's obviously engineering challenges that come with that, or else everyone would be doing it, or limitations. What are they?
So I think there's probably 2 that come to mind. One is, it is a bootstrapped engine. What I mean by that is we have to get some amount of combustion going in the main chamber to then drive the turbine and get that going. So on the ground, we can do that differently than in flight. And that startup sequence is pretty sensitive, so trying to figure that out. We were able to iterate on that pretty quickly to tune that in. But also the thermal environment in the chamber, it's hot. And so if you were to take that temperature gas at its maximum in that chamber to drive the turbine, the inco and the materials that your machinery is inside of there, they'd melt. They're not sustainable. So we have to figure out a way to either cool that gas that comes out or find a cooler portion in that chamber to siphon off from. What some people have tried to do is let's inject fuel. Usually when you inject fuel, you can bring the temperature down a little bit, but that fuel is then not combusted, so you're losing performance. We don't want to do that. So we actually have a Piston Injector Design here.
Bridget was on an absolute roll there, but I'm going to pause to explain some things she mentioned in more detail. since not everyone in the audience are rocket experts, namely around engine cycles and injectors. As Bridget explained, Firefly is the first company to successfully fly a tap-off engine cycle to orbit. A rocket's engine cycle is simply how it gets propellants from the fuel and oxidizer tank to the combustion chamber. At its simplest, this could just be pressure-fed, where the fuel and oxidizer are held at high pressure, which forces them into the combustion chamber when valves are opened. But this limits performance. We need to feed fuel and oxidizer at higher volumes and pressures to increase thrust and efficiency. The gas generator cycle of SpaceX's Merlin engine partially burns the propellants in a separate combustor and feeds the exhaust gases into a turbine, which spins and pumps the propellants. However, this is wasteful, as the products of the combustor are simply dumped overboard, something SpaceX is fixing with Starship's Raptor engine, which is a full-flow staged combustion engine cycle. The Raptor engine runs all of its fuel and oxidizer through pre-burners, with the fuel turbopump running a fuel-rich mixture and the liquid oxygen turbopump running an oxygen-rich mixture. The excess fuel and oxygen from each side then combine in the combustion chamber in their gaseous state where combustion is completed. This is a revolutionary engine, the first of its kind, but look at all the parts required to make that happen. 2 sets of pre-burners and turbopumps, and all the plumbing that connects them. Firefly's Reaver engine simply takes hot expanding gas directly from the combustion chamber and feeds it into a turbine to power the turbopump. Bridget explained that they found a cool spot in the combustion chamber to extract this gas from so the gas doesn't melt the turbine, but she didn't tell us where. However, we can make an educated guess based on what we know about Pintel injectors. Injectors are the part of the rocket engine that introduces and mixes the fuel and oxidizer in the combustion chamber. It's not as simple as just spraying the fuel and oxidizer into the chamber and hoping for the best. We want to distribute the fuel and oxidizer steadily and evenly to maximize fuel efficiency and to avoid combustion instabilities. We also want to atomize the propellants into the tiniest droplets possible to maximize the surface area for combustion to occur. Pintel injectors are much simpler and cheaper than the injectors used during the Saturn V program. The injector of the Saturn V's F1 engine was massive and it needed 2,832 holes, precisely machined into its face, 1,028 for the oxidizer and 1,004 for the fuel, with each of them forming jets of oxidizer and fuel that collided to mix and atomize them. This was an expensive and complicated injector that was plagued by combustion instabilities. Combustion instabilities in rocket engines are basically just oscillations that increase in magnitude when heat released from the combustion amplifies pressure waves and structural vibrations. Basically, the engine hits a harmonic and vibrates. This can affect performance or destroy the engine completely, which happened to the Saturn V's F1 engine during development multiple times. These wedges on the injector plate were actually introduced to break up those waves and prevent resonant pressure waves from building up and sustaining themselves. This plate was heavy and expensive to manufacture. Now, compare that to the Pintel injector, used by SpaceX's Merlin and Firefly's Reaver engines. Both need just one injector for the entire engine. Pintel injectors have 2 concentric tubes that run the length of the injector. Generally, the central tube contains the fuel and the outer tube contains the oxidizer. When the fuel reaches the end of the injector, it meets the pintle, which is shaped to redirect the fuel 90 degrees outwards, where it collides with the oxidizer, flowing perpendicularly downwards. This is a much simpler design, reducing complexity and cost of manufacturing. But the Pintel injector has some added benefits for Firefly's tap-off engine cycle. The Pintel injector's geometry creates 2 zones of recirculation within the combustion chamber, a central propellant-rich zone that helps mix unburned fuel that would otherwise be spat straight out the nozzle throat and not contribute to thrust, and an outer fuel-rich zone that helps form a cooling film around the combustion chamber walls. It's here that Firefly taps off the combustion chamber gases to run the turbopump. A cooler region within the engine that won't melt the turbine blades. This is an ingenious design that no other company has successfully flown to orbit. It removes an entire part from their engine. This is an engineer's dream. Removing an entire component reduces weight, reduces cost, reduces manufacturing complexity, and one less part is one less part that can break. However, this is obviously easier said than done. Taking the gas to drive your turbopump directly from the combustion chamber comes with some issues.
Yeah, I was going to ask of like taking the exhaust straight out of the combustion chamber if there's any issues with combustion instability of things moving around, but
So yeah, combustion instabilities isn't something that we actually see on this, but that brings up a good point that another issue that some people may have is because our fuel, RP1, is actually a hydrocarbon, the byproducts of a fuel-rich mixture ratio can lead to sooting or coking. And because this line goes directly to that turbine wheel, you get deposits on there, which then degrade, which reduce the size of the orifices in there and degrade your actual performance during flight. So you may be at 45,000 pounds of thrust when you launch, but the longer you're flying, the more soot you're building up on that turbine inlet, which reduces your performance. And so there's also some really interesting proprietary technologies that we've developed and also patented that help us not have that issue.
I think I know the answer to this, but are you able to talk about the details of that at all?
Not really, no.
Not being able to talk about things in detail is a pretty common issue on these shoots, but Firefly did take us on a tour of their tank manufacturing. And when I walked into their composite manufacturing facility, where they build the composite pressure vessels, I noticed something immediately. They don't use a metallic liner in their tank. You know, the same kind of liner that buckled on that Falcon 9 and caused that $2 billion satellite to explode. Firefly's Alpha rocket is actually the largest all-composite liquid oxygen rocket tank in the world. Now, I studied composites in my master's thesis, and I knew several people working on PhDs on exactly this subject. Removing the liner has been the holy grail of composite overwrap pressure vessels for quite some time. Linerless composite tanks weigh 20% less than traditional metal tanks. However, while linerless liquid kerosene tanks are relatively easy, cryogenic tanks are much more difficult. Jordy took me on a tour of Firefly's composite manufacturing facility to explain why.
The liquid oxygen, that's when became the real challenge. Why? And the reason is because when you go that cold, let's say roughly minus 300 Fahrenheit, it's very important that when you manufacture the carbon, between the carbon and the resin, you don't have moisture getting into the system. If you have moisture, you have cracks. When you go cryogenic, you're actually going to have ingress of liquid nitrogen, for example, inside, or liquid oxygen inside, that then when it warms up by either external heat or like actually you're accelerating and getting heat, you actually have gasification, you go gas, and it will explode. Like, that's where you crack. And to be honest, that was our biggest challenge for the first years. It's like, how the hell do we make the biggest liquid oxygen tank in the world that flies, right? And that's the one that we made. And to be honest, we broke a lot of tanks at the beginning, and it took a lot of fine tuning. And I think now we have kind of a secret sauce on process, on control, on moisture, on humidity. And then mostly, I think we have a very strong acceptance test plan and capabilities. In-house, we take every single tank after we build it, and we think we have it now figured out because we've flown already 4 and we built many of those. We take it to the stand, we fill it with liquid nitrogen, and actually we load it with first the pressure and second the compressive load that it will see. So when we fly, every time we fly, we know that every tank is good for those levels because we have tested it at least at 10% above the total structural load that it will see, as well as at the max and minimum pressures that it will see. So that's how we screen every single component. And we want to make sure that when we fly, there's no risk, right? That you make sure you've tested that unit to the levels that it will see while it flies.
Is there some danger of crack propagation from testing it the first time and then the second time you actually see the failure happen?
So what we've seen usually is when you break it the first time.
Okay.
Right? So if you test it, and again, because we tested at higher levels that it will see in its life, so this tank, when it finishes its wrap up, that's for not this next flight, it's for one of the upcoming ones. If it were to fail, it would fail here. After that, the pressures and loads that we'll see are lower. So we've seen that we have margin. As well as all these tanks are qualified, meaning that we took them to very aggressive levels at the beginning of the program, and we proved that they would survive excess of those limits.
Okay.
Right? So I think that's why we think it's beefy enough, and if you screen it and you ensure that there's no cracks, there's no errors on that build, you should be good to fly.
You talked a bit about like your secret sauce too, and it's obviously secret for a reason, but are you able to talk about any of the process of actually making a composite structure this large? And obviously behind us is an even larger one. Yeah, like how do you actually make a structure like this out of composites?
Well, first, a lot of analysis and a lot of testing. And I think that's why Firefly, we started small. We started with Alpha, just a ton vehicle. And then we're going now to a 13-ton. I can't talk specifics because we have also competitor vehicles that are trying to do the same thing. But it took a lot of time, a lot of analysis, and a lot of testing on exactly, there's like dozens and dozens of layers of different angles that you have to have. So we had to correlate our analysis with like literally like how you lay it out. Like you're seeing the carbon fiber here. There's different angles, different orientations, the way we do this, and then what things we put inside of it as well. So to maintain not only pressurized and compression, but also shear load. That's one that's very tricky when you get bigger.
Right.
That's why you can start small on composites, but when you get bigger, it's a challenge. That's why there's other launch vehicles that also use composites, but we're the only ones that we have this size right now for cryogenic tanks. On pressurized structures, it's a little bit easier because you're not literally in contact with liquid nitrogen. Mm-hmm. You don't get it to minus 300, right? And that's when on some conditions you get it, it's tough. And another one also, when you fly, you get hot, right? We get a lot of like, so that's why we also had to do a lot of analysis on like, okay, what's the maximum transition temperature that you have on your resin that you're gonna melt it, right? Because metal is much easier, you can take it much hotter, but composite, you can't.
Are you able to talk about what resin you're using?
I cannot talk about the resin I'm using specifically, but I can tell you that, for example, many rockets like us, we need to use Cork to provide thermal insulation.
Just a quick interruption here. We will get back to Jordi talking about the Cork installation shortly, but since he couldn't tell me what resin they are using, I want to hazard a guess for myself because I love material science and getting to deep dive into material specifications is something I miss. In the space industry, phenolic resins are pretty common for high temperature applications. The heat shield of the Perseverance rover was a phenolic resin, reinforced with carbon fiber. Phenolic has high temperature performance, and it also ablates to carry excess heat away, making it perfect for heat shields. But this is too obvious of an answer. I don't think Firefly would be secretive about using phenolic. One really interesting resin I found during my research, which I hadn't come across before, was cyanite ester. It has a really high glass transition temperature of 300 degrees, which is as good as phenolic, but what caught my attention was one key characteristic. It has lower moisture absorption tendencies than other resins. This is absolutely critical for cryogenic tanks because, as Jordi explained, if you have moisture, you have cracks. If you have cracks, you have boom booms. Okay, I just thought that was interesting and wanted to interject, but back to Jordi.
And one thing that we do every time we fly, we actually have thermocouples here. We have thermocouples on our core. We have thermocouples on different locations because the more we fly, we try to understand how does the carbon behave when we fly. And we always want to make sure we have a certain margin.
Okay. Are we able to show the cork?
Yeah.
We can cut and...
This is a very thin layer, but we have a little thin layer of cork that we apply, and that's mostly what we call TPS, thermal protection. Mm-hmm. And we want to make sure that your carbon, again, this is an in-process work, but you don't want to get it too hot. And it's very thin, right? But like this very simple cork, the same way that most rockets put on fairings, we also put on the primary structure to ensure that the composite survives. My dream as a chief engineer is I want to get rid of all the cork. It takes a long time and it's heavy. I have like 700 pounds of like epoxy, like glue and cork and paint. I'd love to fly a naked rocket.
Is
right?
cork a typical material
Yes.
to use in this application?
That is,
okay.
yes. That most rocket companies use cork. It's the one that's very cheap and easy to implement, and it provides you thermal insulation.
And is it ablative or is it literally
No.
just...
Yeah, it just like it provides you thermal gradient between your external temperature and your internal temperature.
Okay.
So I can know here's my carbon that has my carbon in the resin that has a maximum temperature of X. I can tell you what, because then you're gonna know which one it is. But then like you have that specific thickness of cork, right? And it gives me a decrease of like 100 F, for example, right? Depending on the thickness. So we have a lot of analysis on that, and that's why first flight is always scary, right? Because we have a lot of analysis like, okay, that's my temperature, and then you fly. And then you have different temperatures on stage 2, LOX, stage 1, and then mostly the fairing. The fairing is the one that gets hit the most. That's why the thickness of the cork is very thick. But on the tanks, it's much thinner.
And that's just aerodynamic heating on
Yes, aerodynamic heating that you have at different altitudes. Yeah.
Is the cork difficult to source? Isn't there like a cork?
No.
Is this natural cork or is it synthetic?
Yeah, no, it's natural. It's very easy to source. Like you can buy them like in sheets. It's really typical.
Okay.
Yeah, that's the thing. Is like if you want to be a startup and still keep it affordable, that's a very easy way to keep it like that. We're not re-entering and reusing this, right? Just want to make sure you have it.
Yeah. I love that you're using like basically bark from a tree to. Isn't that what cork is?
Yes, that's it. That's it. That's from a tree. You get it. So kids use it for putting the stuff. I just make sure the rocket doesn't burn.
I was under the impression that there was a cork, like a natural cork shortage at the moment, but that's why I was asking.
It might. I'm not too familiar with it. I know that sourcing this is pretty straightforward. You can buy different thicknesses and it's cheap. Okay. The thing is, it's annoying to install. Like it takes time. And if you want to increase production, that's one that we're trying to find ways to actually speed up the process.
Okay.
You know, you want to go to like 6, 12, 24 rockets, right? Laying this takes time.
So that leads into another interesting factor in the logistics of spaceflight that Firefly are working to improve: how quickly they can build rockets. The first generation of alphas that Firefly built were handmade, with the composite layups being placed manually. This is slow work. Firefly's massive, custom-made automated filament winding machine builds their tanks by placing a continuously wound fiber around the diameter of their mandrel. Because the fiber is never broken, unlike the pre-impregnated sheets used in hand layup, the strength of the fiber is never broken, allowing less material to be laid down, and it does it quicker. Manufacturing optimization is going to be a key part of Firefly's future. Being quick to integrate a payload and load fuel isn't much use if you don't have any rockets available to launch. A huge part of the commercial interest in Firefly has been the notion of having rockets available at all times. But that's easier said than done. There are thousands of little battles along the way.
And to get to that point of actually having multiple rockets ready to go and being able to be responsive for a customer, obviously supply chain is going to be a big part of that, and building rockets quickly. Part of that is vertical integration. How do you decide what to build yourself versus what you could just buy from another company?
That's a very good one. And I'd say this also came up from the inception of Firefly. When we started, we looked at the complexity of the rocket and a vehicle, and we saw, okay, which components are very hard, and they are really custom and like the soul of the vehicle. And that's where we saw structures and engines, right? I know there's people that buy them from each other, but it's difficult, right? When you got to put it together, there's always differences, that interface between the structure, the fluids, and the engine. So that's why we said, okay, let's bring that in-house. And we focused on the first years at Firefly to actually develop that engine, that type of engine that we're very proud of. The structures, that's the composite structure. It was also one that we wanted to get together, develop, because it's like the primary structure of the vehicle, right? But then there are also a lot of subcomponents in there, right, that you can buy from the industry, you know? Maybe I won't go into specific components, but there's avionics components that are very good that you can buy from vendors, but they're very expensive, right? And then you think it's like, okay, do I spend $2 million developing it to save $50K per flight, or do I buy the first ones, right? And then there's like stage separation mechanisms. Do I develop my own, or do I lower the risk buying one that's a little pricey, right? So I think the strategy that Firefly took was at the beginning is like, look at the complexity of the systems and which ones are off the shelf that you can buy that you can trust, right? And that's where at the beginning, your first rockets are a little bit more expensive than you'd like, right? But then the goal was get to orbit, right? Demonstrate the capability and start flying. A little pricier than you like, right? Per unit. But then when you actually have NRE, non-recurrent engineering, you get some money invested and you say, okay, I'm gonna tackle this one, I'm gonna tackle this one, I'm gonna bring it in-house. What we have seen over the years is that it's hard to rely on vendors, right? Because again, we are not Boeing or Airbus that buys hundreds of thousands of components, right? You buy little. And sometimes you have a failure and then go in there and say, hey, why did that fail? Right? It's like, oh, you know, it's like, you're buying me 20 rockets, right? It's like, I don't have time to give you support, and we don't know the design, so it's hard for us to understand. It's like, okay, why did that fail? And what we've realized over the years that critical components that are a little more likely to fail, it's better for us to bring them in-house, because then when something fails, we have the engineers that know literally the printed boards that we designed. Why did that fail? We can actually go mess with it, learn it. It's like, oh, that's it. Then we test it, we rebuild it in 48 hours, we fix it and put it on the rocket, and you can go again.
Do you have any examples of that happening that you can talk about?
Yes. So we had some components, I won't say specifically which vendor and what, but we had a specific component, actually that was for Victus Nox, that we had it on the vehicle, and it was a commercial off the shelf. It had flight heritage, and we had been using it, but we had an anomaly on the ground, and it failed. And then we tried to troubleshoot it, and we reached out to the vendor and say, hey, okay, what's going on? Why did this fail? You know, what electronics, what's the problem? Oh, send it back, we'll look into it. And then they said, oh, you just need to buy a new one. It's like, I can't, it's inside the rocket, right? It's like, I need to fix it. And it's like, oh, so yeah, okay, let's send it and we can put it in an engineer. It's like, no, you don't understand. Like, this is very important. Like, we have a timeline, we need to go. And again, that was not the day off, right? It was like 2 months before. But then we were at the point, it's like, okay, we just can't depend on these guys to actually fix our problems, right? So that's where we said, like, okay, enough, right? We had Blue Ghost, our lunar lander that was on the site, developing its own internal component. It was pretty similar. So we were like, okay, that's it. I put together a team. We were at the end 91 people that took that specific component, and we worked every day, every night for, no joke, 41 days, 91 people. And what we did is like, we actually took that Blue Ghost half design and we said, this is flying in 2 months. And the response engineer said, sorry, what? Like, I was supposed to have 6 months. They said, 2 months and you're going and you're primary for this mission. Right? So then we put a team together, we got a lot of engineers, and I love to get a bunch of like young engineers, like, you're in charge of like the design, you're in charge of the testing, and we had to not just slap it on and fly it, right? It's like you have to qualify it, test it, build several units, you know, take it to thermal cycling, shake it, vibe it, shock it, right? And it's like, make sure that this is not gonna fail. So that's why we did that, and because in-house, we can first make parts, we can make boxes, we have the engineers to actually design boards. Right? So we had the guys actually making the board, and we had a failure in the middle of the development that the thing crashed. I was like a weekend off. I took a weekend off with my family, and driving up, it's like, it failed. It's like, you kidding me? Redesign, right? And it was like redesign on a Sunday, and Monday we actually had another one. We got a new board, put it on, and did again the whole process. Like when we told the Space Force that this failed, they were like, oh my God, that's an 8-month delay. It's like, hold my beer, right? And it's like, no, we're gonna do it. So actually, we went crazy, we did it, and again, like that was very exciting because the team took ownership, and I think that's how Firefly was able to succeed. It's like these guys knew that without them and without taking like ownership, they would not succeed, right? And that's why, like, I honestly had like 24-year-old guys going at 5 a.m. on Saturday, and it's like, what are you doing? It's like, can I go inside the rocket to check something out? And I looked at it, it's like, okay, go for it, right? And they were testing things out and coming up with ideas, and then we brought that design, and actually we qualified that design, and we flew that design for Flight 3, right, for our Victus Nox mission. And then it's what we fly for now on, for all the missions. But that was a success story that, like, sometimes it's hard to depend on customers, on partners, and it's better if you own it, because then you can fight your own battles. And to me, at the end, it's own your own destiny, right? If something fails, you can make more, you can have it, you can fix it, then you understand it, right? If you don't know what the box is made of, what the connections, like, it's hard to troubleshoot.
This story again just highlights how important it is for Firefly to have all their facilities and staff working in close proximity to each other. It really allows them to quickly iterate and solve problems. This is a huge part of what helped Firefly break that 24-hour record. But everything we've spoken about up to this point barely touches on what went on during those 24 hours. When Firefly got their notice from the Space Force, several things needed to happen. Just think about how complicated this is. They received the information on what orbit they were targeting with only 24 hours notice. The guidance and navigation team needed to figure out the trajectory and test it using simulations on the ground. These simulations are actually run on the rocket, so all of the relevant parts actually actuate. There just isn't any propellant. The rocket is just being made to believe it's flying by the computer. Firefly had predicted the most likely orbits that the Space Force would want and had pre-run the simulations so that they could be prepared when the call came in. When the call came in, they loaded this data and performed one of the dry run tests. Firefly also needed to deal with all of the bureaucracy associated with the launch. They needed to fill out paperwork for the FAA, exclusion zones for the launch needed to be established and communicated to the relevant authorities. None of this could have been done without cooperation from the Space Force and the FAA. This is just one step, but integrating the payload to the fairing and mating it to the rocket with only 24 hours was a whole other logistical challenge.
And you spoke about payload integration too, that you've come up with some designs to make that quicker. Can Can you talk about that too?
Yes, when we won that contract for Victusnox and we engineering team got that, it's like, you're crazy. Like, we can't do that, right? It's like 24 hours. Like, we got to, and the goal was we got a call, and then we had 24 hours to put the payload on the fairing, encapsulate the fairing, and that's in a clean environment in a room, and then roll it out and mate it with the vehicle, lift it, and launch it in 24 hours. And the key was that we had a window of like 3 minutes, I think, that we had to hit. Because the idea was like you had to end up in a specific place in space, right? So like it had to be depending on what time of the day we had.
Okay.
Right? So for example, design decisions is when we first got it, was that we can't do it. So we had to design hardware around it. So we had to design what we call ground support equipment that actually held the fairing, held the path, and allowed us to first load and then rotate, do the final checkouts, and actually hold the fairings, put them on and mate on that configuration. And then once we had what we call the payload-based assembly and the two fairings closed out, we had to then create also what we call an environmental control system. You need to make sure that your satellite is always first absolutely clean. You don't want to have optics that get dirty with dust, or you don't want to have moisture, right? Let's say you have cameras on your system or star trackers, right? If you have moisture on a system above 60%, you're done for the day. You can't launch, right? So we had to develop ground-side systems that could actually go and pump heat and cold, depending on the day, and then control moisture, which, in Vandenberg, to be honest, was a challenge, right? Because we had not done that. And again, like, develop that from scratch, like, we had the engineers going crazy on it. So we did that, and we did lots of testing, and then we had to go and mate. And the thing is, we had never mated before on the pad. We usually, like others do, you actually mate on your horizontal integration facility. That's how we did Flight 1 and Flight 2. So you had to just go, put the payload on, mate, and then go out, and then launch. When you install your vehicle and you do the whole static fire, meaning we fully loaded and we simulated everything is good, you have to take it out again and install the payload and go back in. You waste 2 weeks because there's 30 or so fluid connections that you need to reconnect and check. And it's not just, ambient helium, right? You're talking of cryogenic helium, cryogenic liquid oxygen for stage 1 and stage 2. So all of that needs to be rechecked. So we have to develop a system to outside, even in rainy day and windy day, that we had a way to actually go in there and mate. And to be honest, it was a challenge. We made it here 6 times before. And we were like literally timing, counting bolts. We got to a point that we had to slightly chamfer the bolts to help us go faster on entering, because you have like 120 bolts that you need to go in, right? And people had like, you had 20 minutes, right? And the technicians like, are you kidding me, right? So they were all like, go in. It's like, no, so adjust it. And it's still a big rocket. So you have to like adjust the going in and make sure that all of those were lined up. And then you gotta go carefully putting the fasteners as well, because you're going to a composite structure, so we don't have like inserts inside, right? So like you gotta be careful, because if you go too fast, you break them and you pop them out, right? And then we also had to make calculations of how many bolts could we miss in case like some were actually losing the threads or even failing, because you can't go correct for that. So we had to do a lot of analysis on that and prove what was good. But yeah, that was a real challenge, and the teams did amazing.
Almost sounds like you'd need to consult with like an F1 pit crew team to find out.
And no joke, but we have some F1 guys here.
Okay.
Yeah, and they're from Europe and from here, because it's that sort of level. It's funny, I consulted for Ferrari many years ago in Italy. Yeah, and it's kind of the same mindset. Ferrari, every 10 milliseconds of savings for a lap, you gotta go implement. Right. We had the same thing. Every 5-15 minutes you could do in save time, you could go implement. And what we did good, I think, is we worked with the technicians and the integration engineers and the design engineers. Said, okay, where can you save time? So we would do one attempt, and everybody would take notes. Say, hey, I can shave 5 minutes. I can shave 15 doing this. If you change that, we can actually do it. So we spent like 5 months or so, like trying things out on how to save time. And the beauty now is that after we've done it once, right, it's like we realized that we can do better, right? And the fun thing is like we did it, and for us, like, damn, we made it. Like, to be honest, it was like crazy, right? Like we didn't think like the previous record was 21 days. We thought 24 was crazy. And I'm sure the Space Force also thought it was crazy, right? But the challenge was there. And once we hit it, I go down congratulating everybody, and say, great job, guys, great job. It was awesome. And then the tech is like, man, I think we can shave 2 hours. I was like, stop it, But they were all so excited. And that's why actually for every Flight 4, we did improvements too. And the idea is to shave it, right? Because there's a lot of customers and governments that are asking for like, hey, can you respond in quickly and go up there?
Firefly has achieved a lot, but still has a lot to prove. Since filming these interviews, they've successfully launched to orbit a second time with the Noise of Summer, but they are also working on their lunar lander for an upcoming moon landing attempt with the Blue Ghost mission later this year. The Alpha rocket is a small rocket capable of carrying 1,030 kilograms to low Earth orbit. For Firefly to gain more market share in the highly competitive space launch market, they need to develop heavier lift rockets. They are currently developing a medium lift rocket in partnership with Northrop Grumman, which is being designed to carry 16,300 kilograms to low Earth orbit, a major step up from Alpha, but still using that tap-off engine cycle for the larger Miranda engines. The first flight of this medium launch vehicle is slated for 2025. The space industry is so competitive. When I'm placing my bets on which companies will be successful, I usually look first to the talent in their engineering departments. I was incredibly impressed by both Bridget Oakes and Jordi Garcia, and I wish I could have included more of their interviews in this video. It always feels wasteful to leave the knowledge they share on the cutting room floor. So I've uploaded their full interviews on Nebula for anyone interested to hear them. Before I go into an entire spiel about how great Nebula is, I know many of you are sick of signing up for yet another subscription service. So if you simply want to support our channel and get lifelong access to all of Nebula's exclusive programming, we are offering lifetime memberships for a limited time for $300. Unlike other subscriptions, you can buy once and never pay again. This helps us fund original programming like our 5-part Battle of Britain series, where we recreated the central command room of the Battle of Britain to show in intricate detail how Britain won their most impactful victory. We show you how incoming raids were plotted on the huge central map with color-coded tiles, and how the commander kept track of what squadrons were available using a light-up board mounted on the walls. We spent over a month recreating this room using archived footage and photos, an investment of time for a single animation asset that we simply can't afford on YouTube. For less than the price of a cup of coffee per month, you can get access to all of Nebula's originals, along with our entire catalog without any ads. You can also easily download videos to watch on the go. This channel depends on the funding Nebula provides. If you've been subscribed to this channel for more than 3 years, you've seen the huge increases in production quality that Nebula has facilitated. Growing from 2D animations that myself and Mike taught ourselves how to do, to having a full team of incredibly talented 3D artists that rival any TV production. This is expensive work, and we would love to grow our team even more, something we can only do with your support, as YouTube ad revenue simply does not cover the bills. Last year, we actually made a small financial loss for 3 months in a row. YouTube is simply a volatile platform where we depend on the whims of advertisers. Nebula is our life raft in a volatile sea of social media. This is a common theme across YouTube creators. Nebula's goal is to enable and level up our entire roster of creators, to remove any financial uncertainty that forces us to rush projects, to remove the algorithms that force us to analyze data points instead of what really matters, the audience on the other side of the screen. So, if you want to check out all of that fascinating exclusive content on Nebula, go to nebula.tv/real engineering or click the link in the description to get 40% off our yearly subscription today